a master degree.
This meeting is being recorded.
She has a master and a PhD in analytical chemistry applied to vibrational spectroscopy and chemometrics. She has 10 years of experience in research and development experience using infrared and Raman spectroscopy applied to food, pharmaceutical industry, PAT, patch analytical technology, biological samples, and soils. She is also an expert in multivariate models for calibration, classification, and quantification, always focusing in chemical data. And currently, she is a postdoctoral research in chemical analysis using portable near devices applied to food soils and development of chemometric models. She's also working as a specialized advisor on chemometric brain company, and she's also an expert consultant on chemometry for need data in other projects and in other companies. So Marina, could you start now?
Yes, sure. So thanks, Felipe, for introducing me. It's a pleasure to be here. So I would like to thank you for the invite and as well for the whole organization of this event. And let me know if you can see my screen. Just a second. Yeah.
Yes, we can see your screen.
Okay, thank you. So can I start?
Sure, please.
Okay. So hello, everyone. So it's, as I mentioned, it's a pleasure to be here and talk a little bit about my experience on vibrational spectroscopy, especially in NIR applications to solve these industrial demands and also for daily problems. So first of all, I would like to show you some talks that I will discuss with you in this talk. So I will explain a little bit better my background and knowledge on the academic side and the industrial side as well. After, I would like to show some instrumentation, NIR, benchtops, and handhelds that I've been used for so long. And after that, my idea behind this talk is to show you different applications with NIR. So I will talk about some cases and in more detail about, for example, investigation of bread agent, because I think it's a very interesting application of NIR to understand and investigate some chemical process. I also talk about quantification of hydrocarbons in soils and discuss briefly about some chemometric softwares. And to conclude, I would like to show in a briefly way as well some cases of homogeneity control of suppliers and process controls applied to food industry. So I'm chemist, as Felipe mentioned before, and since my first years at university, I've been in love and passion for chemometrics. And because of that, I decided to went through to my academic career. So I got my master's degree in analytical chemistry. My focus at the time, it was in Raman image spectroscopy applied to dairy products, specifically for powder milk and supplements for child. And after that, I got my PhD in this vibrational spectroscopy applied to food and chemometrics from University of Campinas in Brazil, and also carried out a part of University of Duisburg, Essen. And nowadays, I'm a postdoctoral research, and my main focus is try to use as much as possible different handheld NIRs and evaluate the devices and also the applications, use chemometric tools, and also to apply to food and soil samples. I also had some experience from private companies and industry. So from example, from pharmaceutical industry, I I was part of a team that was implementing this PAT, process analytical technologies. And that time I was using Raman and mid-infrared to evaluate mix efficiency directly in Blender machines. So for this proposal, we attached the Raman probe directly on the window of these machines, and we acquired some spectra during different times. So for example, if you have a process with 4 different addition steps, the time is zeros. We fill it up the machine with raw material A and B. So we start to blending, and after 5 minutes, we add a new material C, start to blend it again, and do this for the material D and for material E. So it's very interesting to analyze how the homogeneity is inside these machines. And for that, we build this control charts. So control charts is basically, we can see the confidence area defined by these 2 red lines. So if the sample is under control, that means if they are homogeneous, the samples should appear inside this threshold. And if the sample or batch is out of control, the sample should appear outside. So it's expected for the beginning, for example, the beginning of the process, and where we don't have too much time, or we don't have time enough to mix properly the materials, or the samples are outside. And after some time blending and mixing, the samples, the batch become more homogeneous. So we do this to understand the different steps of additions. And another application with this PAT, it was to quantify some API contents and a high concentration range. So for us, we built this calibration using, for example, 90% to 110% of API. And for that, we used some batches that were reproved by chromatography analysis, and other batches was approved for chromatography analysis. So on the right side, you can see different types of pharmaceutical process. So wet granulation, dry granulation, or direct compactation. And our idea was acquiring spectra after the first mixing, the first blending, and before the tablets. So in this way, we can evaluate the homogeneity and also to build the calibration to predict the API. So it's important to mention here, the idea behind of this project, it was to develop a method which will capable to select the most likely successful batch. So when we are working pre-formulation, we are developing many formulations. And if we ask for the analytical department to run all these new formulations by chromatography, they will be very mad with us. They will not do this. So the idea here, it was to develop a screen method to select the good ones, the most successful ones, and go ahead to the further chromatography analysis. So it wasn't use NIR, but the idea here, it's very nice. So I also had some experience from photonic company. So in that opportunity, we are focused in develop the hardwares based on NIR and RAMA as well for medical diagnostics. And nowadays, I'm working for the chemometric brands, and I will explain a little bit later. So NIR technique, it's a very well-known techniques, and because of that, we can find many brands on the market at the moment. And from the benchtops, I just would like to show you which ones I'm using at the moment. So the Bruker instrument, the FOSS, the Antares from Thermo, and also PerkinElmer. But my main focus, to be honest, and nowadays, it's try to test different handhelds or portable device, such as Trinamix, Viave, Microneer, and also on-site Viave. Some near scan from Texas and from InnoSpectra, some systems from Supplier, for example, the Neo Spectra device, some MEMS systems, and also from spectral engines. And the first application that I would like to show you, it's about the authentication of plant-based supplements. And in this case, we are interested to see if the plant-based protein powders, many labels claim like free gluten, free soy, free lactose, and we would like to confirm that using a one-class methodology. So we use the one-class partial least square for this. And also after that, our second task was to try to identify the adulterants inside. So as source of lactose and gluten, we used, for example, wheat and whey. And we bought many different brands on the market from these plant-based proteins and with certificate as well. And we adulterate directly on the laboratory in a range between 0 and 40% with soy, whey, and in wheat. And we acquired the spectra, used the Antares 2 in the diffuse reflectance mode. And we can have a look on the spectral profile here. We can see from the 6,000 to 7,000, the spectral profile shows a quite difference. So we can expect at least a good separation for this application. So our first question is, this is a authentic sample. This is a plant-based protein. And for that, we use this OC PLS. I split the data set. We had 50 target samples into calibration data set and validation data set. And when we use these one class methods, it's important to have in mind that to build the acceptance area or to build the model, the one class method use only information about target samples. So the acceptance area is in fact this left bottom square. And so if a sample is located inside of this confidence area, the sample will be assigned as a target sample. In our case, will be assigned as a plant-based protein. And if a sample is assigned outside of this acceptable range, so we can say this sample is adulterated. And for this prediction data set in picky color here, I used over than 200 adulterate samples. We achieved 100% for sensitivity and specificity. And if you will remember, the spectral profile from the samples, they have many differences. So it was expected to achieve this good separation. After this first question, now we are going for the second question and try to identify the adulterants using now a multi-class strategy, in this case, a PLS-DA. So in figure A here, on the left side, we have the calibration made with 4 classes. So the first class is the class in red with 35 samples from plant-based, pure plant-based protein. The second class in green, it's formed by third plant-based adulterate with soy. And the third class in blue, it's adulterate with wheat. And the fourth class here in cyan is the samples adulterate with whey. And the right side, we have the prediction data set. And we also achieved a good results, and we can justify these results by looking at the VIP scores. So when we look for the variable important for each class, we can see sometimes some bands appears for all classes, but we can find specific bands for a specific class. So this is a very good strategy to show why we could separate very well the samples in this case. The next application in this one I would like to discuss in more details is the investigation of braid aging or braid styling. So this is a very huge problem for the economy, because when we have this process of aging, the bread changes some texture, some flavor, increase the hardness, and because of that, we lose many kilos of bread per year. So it's good to understand the chemical reactions behind this effect, and to understand that we need to understand the most bread are made from wheat, and the wheat is made up from starch. So the starch has a very important role in the system, and the starch is made up of this amylopectin and amylose. So when we have these fresh flowers, for example, we can see a very well-defined structure, amylopectin and amylose. So this is very characteristic of crystallinity. And when we go to the loaf or fresh bread, because we add some new ingredients, for example, as water, and we heat it, the system goes to process called gelatinization, and this gelatinization decrease the level of crystallinity in the system. And the last step is the stale bread. So we can also have now a new well-structured, organized. So we have in this step the heterogradation of starch. On the left bottom, we can see, for example, some amylose chains interacting with water. And after this water decrease the content of water by diffuse from the core to the crust or by evaporation, what we have is a new structure, amylose. The same idea we can apply to amylopectin. So first it is interacting with water, and after the evaporation, for example, now we have a new structure. So all of this will impact in this aging process, and we would like to go deep to try to understand from the point of view of chemistry what is going inside. So for that, we used the Neo spectrum scanner from Supplier, and we cut the baguette on the half and put directly on the window scan and measure for 48 hours directly. So in the first, this first plot in the left side here, we have all the 48 hours spectra represented, and a very good tool to analyze this kind of challenges is to apply this involved different spectra. In this way, we can see which bands is point up, which bands is point down, and try to understand previous what's going on in our system. So we have applied to correct this scattering, this EMSC. We decided to truncate the spectral range between 6,000 to 4,000, because in this range we can find the narrow bands, so the well-defined bands, to try to assign some sequence of events. We also split the data set into first 6 hours, and from 6 hours to 48 hours. And you will understand why, because we have different process in these two data sets. So the peaks, for example, points up, it's 58, 51, 51, 58, 4703 and 4346. They are related to the crystallization of starch, and the peaks point down in the involving difference plots are related with the decrease of water. To understand it deeply, the system we had applied to the cause is two-dimensional correlation spectroscopy. I will not explain deeply the equations, so you can have a look in the Isao-Noda papers. But basically, to the cause, it's format using two components, so synchronous spectra and asynchronous spectrum. So the first components, we can see some simultaneous changes of spectral intensity observed for two different wave numbers. And from the second one, we can try to predict some sequential changes of spectral intensities. From these two decals, we got these two maps, one map for synchronous and another map for asynchronous. You can have a look here in the x-axis is wave number, Ni1, and y-axis is wave number, Ni2. So that means for each peak that we have here, this peak is formed by two wave numbers. And we can select the most strongest signals in both maps. And to understand better the interpretation, we built this table. So when we have blank peaks, that means positive signals. And for synchronous, when we have positive signals, for example, let us see the number 4 here. If you have a positive signals, that means the band 4964, if 5311, they change at the same direction, or they goes down or they goes up, but it's the same direction. When we have the shadow or blue color here, we have the negative signal. So for example, number 1 here is negative. That means these two wave numbers, 58, 51, 53, 11 centimeters minus 1, they change in opposite directions. So one should go up and another should go down. So we do this interpretation for the whole numbers here. And the only exception here, it's for, let us say, I will take this case number 5. When we are interpreting the asynchronous plots, when we have positive signals, that means the change occurs for wave number 1 occurs before then wave number 2. And when we have the negative signals, the change for wave number 1 occurs after for wave number 2. So when we do this interpretation in this table, we can try to predict it, or at least suggest a sequence of events. And from this table, we got this sequence for the first 6 hours. So that means the change occurs before for CH in starch, for crystallization CH in starch, followed by the weakly hydrogen bond in water, followed by the crystallization of OH in starch, and followed by a strongly OH bond in water. When we are going to do the same thing now for the second data set from 6 hours to 48 hours, we can see the maps now are quite different the previous one. So we can expect it, the sequence are quite different as well. And we do the same thing. We selected the strongest peaks. We built this table, and now we have a new band here. So this new band, it's also related to CH from starch. And now, because the high intensity from 6 hours to 48 hours, we can observe this new event, this new phenomenon. In this case, now the sequence of events change a bit. So the first change occurs first for OH bonds in waters, followed by crystallization in OH in starch, followed by the crystallization CH in starch. So as conclusion, for example, for the first 6 hours, the starch crystallization is more dominant than water evaporation. And from 6 to 48 hours, the water evaporation plays a large role than crystallization. And why this is so important? Because sometimes for the food industry, if you understand the process in our food, we can add some enzymes to try to stop the crystallization, or we can add more moisture. So to understand what's going on in our process, it's very useful in this way. And also it's very nice example to show how a handheld NIR instrument can be easily performed on site, and how we can try to understand this chemical process. And now I will change for soil a bit, because I would like to show also how can we apply this NIR handheld device to quantification in ppm, hydrocarbon in soils. In this case, we have samples from different sites, sites A and B, and one more or less around 150 samples, not too much. And when we plot the PCA here, we can clearly see a separation between samples from site A and samples from site B. In this case, when we have samples with different oranges, this can generate non-homogeneity and non-linearity. So when I try to apply directly the traditional PLS, what we see here, for example, we can make different regressions, right? One from the group in blue and another one from the group here in pink. And if you have a look in the R square, also it's like 0.56. So this is not a really significant regression. And to try to minimize this type of effect, to solve this issue, we have applied a locally weighted PLS. So in this case, we can see now we have only one regression, and our R squared is around 0.98. Another important thing is to evaluate the root mean square. In the first case, it was around almost 4,000 ppm, and the second one it's around 1,000 ppm. And I also would like to highlight here, we are trying to quantify samples with like 30,000 ppm, 20,000 ppm. I'm not talking about to quantify values like 5 ppm. So for our project, it's very acceptable if you have calibration, global calibration. That means using samples from different sites and get errors around 3,000 ppm. So because this is, again, this is a screen methodology, and this is, for us, it's enough. About the softwares, I'm using a lot of the Scrambled by Camo. It's a very completely software and also sometimes very complex. So, but you can find many options inside. And I'm using just for PCA in PLS regression at the moment. The other one that I use it a lot, it's MATLAB. So in MATLAB, you can get some toolbox. For example, the MCR toolbox and DataDrive Synca. Those ones are free, so you can use directly on MATLAB. And also, of course, the PLS toolbox from eigenvector. So we can find the PCA, the PLS regression, the discriminant analysis, PLS, and also this locally weighted approach also in PLS toolbox. Nowadays, I'm working as a specialized advisor for a chemometric bank company. So our slogan is digital quality control for the food industry, and we have our own software. And this software was built trying to make easier the life for industry. So you can find the most important chemometric tools for industry, for example, PCA, PLS, this local PLS, you can also find in this chemometric brain software. And our idea here is also try to make easier the interpretation of results, because when we are working directly on industry, time is money. So we try to develop solutions for practical problems. And I would like to show some examples of that. So for example, the control analysis of suppliers. If you are working with more than one supplier, in this case, 5 suppliers, you can ask which supplier would I selected, for example. So we can do this buying a PCA. So this is a PCA, this is the score for the samples. And for example, here in supply number 4 in orange, we can see the samples or the batches are very similar. So the distance between each other is not big. So we can say they are more consistent and they have less variability. So this could be a very good choice for you. Or for example, if you are working with a supplier number 2 here, you can see they are very similar to supplier number 5. So if you're working with 2, maybe you can also choose the number 5, and the process will be not so difficult to get the same results. So this is a very good example for industry to control of suppliers. Another example that we can apply for PAT as well, it's the optimum blending time. So in this case, we have 4 minutes in green ellipses, 6 minutes for the red ellipse, and 8 minutes for the blue ellipses. So in this case, the optimum blending time, it's 6 minutes, because again, we can see the homogeneity of the samples. And this is a very good example how to use NIR on the industry, because sometimes, for example, the customer are using 10 minutes to blend, but this is not necessary. So you can evaluate these factors, these parameters, and you can decide, okay, with 6 minutes, I achieved the homogeneity that I want to continue. So I will cut off the time that I'm used to blend in this for 6 minutes. Another example, very good to example in the food industry. Sorry, it's for example when you're working with different formulation or working with different recipes, and from the tomato paste, for example, they are working with different bricks and also with different types of process with different temperature. So it's possible to build different models that you can see. For example, in red one here, we have bricks with value 28 at a temperature 30. If you go down to green one, now we have the bricks with 28 as well, but now with a different temperature with 38. So we can also control the process if you are changing some parameter, if you're changing some temperature or bricks or whatever. And other good example as well, for example, if you are working with a mixed ingredient, so you have 70% of a mixed ingredient and you have to fill it up, you have to complete it with 30% of your maltodextrin, for example. So if you change the suppliers, you can instantly detect this. Sometimes the suppliers, they didn't report this change, and this can be a very problem for the final product. So it's very nice if you control your process since the beginning, so you know exactly what you are mixing, you know if you have to stop before you run the raw process at the industry. And of course, we can also quantify some nutritional parameters, for example, proteins, fat, dry matter, using local PLS. That means we are using it's also an option to use the traditional PLS as well. But if you realize that we have some non-linearity, if our samples are not so homogeneous, so we can try to use this approach, try to correctly the calibration. So this is more or less what I have to say. Maybe I spoke too fast, but my idea here, it was to show different applications with NIR and chemometrics as well. And please feel free to ask me if you have any questions.
Thank you very much for the terrific presentation, Marina. If anybody have any question, can just type these questions in the chat. Okay. Marina, you said a very good phrase for me. Industry time is money. As in general, I have some PhD students, they say, oh, you need to use YAR because it's free, blah, 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 blah. But for the industry, that doesn't apply. And you say the phrase that I use a lot. The industry, they want the buttons for someone to solve a problem fast and go for the next problem. I totally agree with you. You touch in a very good point. in my opinion, it's about the use of one-class models. I believe we have a lot of people here that are not so common with this kind of approach about one class. Could you just say in a few words when and just a few words when and how we should use one class problems instead use binary classification like PLSDA or something like that?
Yes, for sure. This is a very good question. So, of course, there are different points of view about these questions. But for me, for example, one class method we can apply when we have some questions about authenticity or origin geography, because sometimes it's very hard to sampling in a very representative way. So if you are trying to say if this sample is authentic or not, it's better if you try to build your model only using info about that target class. So, and for example, for PLSDA as a multi-class method, when you know, for example, I was trying to identify as adulterant soy, wheat, and whey. So I had an idea about these three classes. I knew it that these adulterants inside of my samples. So for this kind of approach, I would suggest PLSDA or any multi-class method. So for me, this is the basically difference when you are working with authenticity or geographic origin, you should try at least to apply these one class methods.
Okay, thank you very much. We have a lot of questions in the chat. So first question is from Claudia. Thanks for the nice presentation. Could you detail a bit more how you set up the PLS inside the one class PLS?
Yeah. So actually, this one class PLS, it's a new. It's not a toolbox that you can click the buttons, but you can download these files. And one class PLS, basically in the vector for the reference values, you have to put if your class is 1 or 0, more or less very similar to PLSDA in this way, but the regression is different. So the regression, it's only basic if you're looking for your target samples, it's 1. Let us say if you're working with adulterate sample, doesn't matter, this will be 0. So the vector for the reference values now it's different. It's 0 and 1.
Okay. I have another question from Philippa. What statistical techniques do you find the most successful for monitoring blend uniformity?
This is a good question. I can say the easy one. Okay, the easy one, of course, it's PCA. Easy one. You can see many things, but I like the control charts, multivariate control charts, to be honest. But of course, you need to develop a little bit better your model. But from PCA, you can see many things, many trends. So from industry, PCA, it's very okay. For me, I didn't see difference from, for example, when I was working and at pharmaceutical company using this control chart, and now for food industry. So I would say PCA.
Okay, thank you very much. That's the next question. Sorry if I pronounce wrong. It's Yuan or something like that. Thanks, Marina. Very interesting. Just a question regarding the handheld here. Have you experienced any downside from using handheld devices in practical situations?
Yes, when we are using, for example, NIR, handheld NIR, it's very useful because we can use on site. It's very practical, but we cannot compare yet with a benchtop one. So if you need some very signal, you can compare signal to noise sometimes, and or the spectral resolution. So of course, it's not exactly the same, and depends of the spectral range. It's hard to find the NIR handheld NIR with the whole range, except the Trinamics. You have a a quite large spectral range. It's almost the same as the benchtop one. So you have to analyze all these topics. So you have to select the right range, spectral range. Sometimes not good for your application, or sometimes the resolution is not so nice. So yeah, of course, there is some problems.
Thank you very much. Last question from Gary. Did you try using some type PF? I don't know what does mean PF here. Classification analysis for the first problem you discussed?
Yeah, I don't know what is PF. If the okay.
Okay. Yeah, so did you try using some type of classification analysis for the first problem you discussed?
Which one was the first problem? Sorry, it was at the pharmaceutical or the authentication of plant-based
That's right.
protein powders. Yeah. So for classification, I tried to use the PLSDA, but it was classification of adulterants. But because I also add the class of plant-based supplements, so we can also see classification applied for this kind of problem. But I use it both, I use the one class for authentication, and I double check it with this PLSDA for classification.
Okay, thank you again. Very well. I would like your opinion about handheld device, because as you say, a lot of people, I believe now, they want to, instead buy a benchtop instrument, they want to buy a handheld device, and of course you have a lot of advantages and disadvantages. But do you believe in academia, like universities or research centers, we are moving to use handheld devices instead of benchtop? Or do you believe these would be more for industry? What do you think about that?
I think this is more for industry, but nowadays, even for industry, they are using benchtops yet. So of course, for PAT projects, on-site projects, they are using the handheld, but yet for quality control of raw materials or other analysis, they are using yet these benchtop ones. So I believe for academic, we will still have some benchtops instruments, but I hope maybe the price, because now we have many handheld device, the price become lower, and maybe this can be a good thing for academic and industry as well. But I think in the future, of course, many people will start to use handheld, but I still believe they will still at least one benchtop machine with them.
Okay, thank you. Another question from Maria. Did you try using some of your analysis deep learning methods? What is your idea about it then?
No, I didn't yet. Actually, we are working with a data set not too big. So specifically for these soil samples, I was thinking to use other techniques, but because we are working only with like 150 samples, not a big data set yet, I prefer to use something to correct the nonlinearity with PLS. But of course, if in the future, if I have a big data, maybe I can try to think about other types of chemometrics or deep learning.
Okay, thank you. Sorry, I just missed Claudia's question, so I have another question for Claudia. Do you actually use the handheld instrument held by hand, or as opposite to a tripod or something like that? And would you comment on how sensitive the different instruments are about regarding to the movement, vibration?
Okay. Yeah. For example, when I was measuring soil, I really used the handheld by hand. But for when I was investigating bread, I just left it on the table. So it's up to you. You can use it. I mean, there's not so sensitivity. I mean, obvious. You don't have to move and try always to have the same distance between the scanner and sample. But if you don't move too much, it's not a problem to use by hand. And how the sensitivity. Yeah, so I would say, of course, it's lower than benchtop instrument for sure. But we are working now in try to compare some handheld instruments to benchtop ones, and we are achieving a very good results. So I'm not trying to sell any device here, but for example, specifically for this Trinamics, because they have the raw spectral range, we can compare with some benchtops, and it's very quite result. So of course the sensitivity is lower, but I'm very believing that the industry, the hardware industry, is moving very fast to try to minimize this effect.
Okay. Okay, so thank you again, Marina. Do you have any other questions? Okay, I believe no. If someone has question, you can send an email to Marina. And yeah, thank you again, Marina. It was a terrific presentation. You give so much more details about the industry. I believe Philippa have another question. No, sorry, she's just clear. Yeah. So thank you very much for our presentation again, and it was very nice to stay with you here this afternoon. Okay.
Yeah, thank you both. So if you are interested about any application, you can send me an email. I know, for example, because it's a quite I wouldn't say new, but it's a very different approach. So I would like to show, because I try to show the NIR can be used for classification, for quantification, and also as well to investigation some chemical process. So if you have any questions in the future, you can send email and feel free. Thanks a lot, Felipe, again.
Okay. So thank you everybody here this afternoon, and see you in the next meeting. Just a reminder that if you want to rewatch the meeting, you can just go in our page in Vista Milk Spectroscopy, and then you can get the link in YouTube.